Let's draw ourselves a rectangle to represent some structure, and let's pin that rectangle at the bottom left corner. And then let's apply some forces to this structure. Let's go over here to the top and apply some downward force, which we can call force 1. And then let's go over here to the right and apply some leftward force, which we can call force 2. And at the bottom, we can draw some upward force, which we'll call force 3. And then let's add one more. Over here off to the left, we'll draw a rightward force, which we'll call force 4. Now, if this is a good structure behaving the way it should, then all of these forces would cancel out and they wouldn't actually move this structure at all. And the way we write that is the sum of all forces add up to 0. And this idea is known as static equilibrium. Where all my left and right forces cancel out and all my up and down forces cancel out. And so if I am applying a rightward force here of 5 pounds, then this leftward force also has to be 5 pounds to cancel it out. And likewise, if I'm applying some downward force of 7 pounds, then this upward force has to also be 7 pounds to cancel it out. And so another way to write this then is to say our left forces are equal and opposite to our right forces. And all of our up forces are equal and opposite to our down forces. And so this sum of all forces equals 0 actually breaks down to our horizontal forces. The sum of all forces in the x direction equals 0, and the sum of all forces in the y direction equals 0. And what forces do we have in the x direction? Well, we have force 4 going to the right and force 2 going to the left. And so the only way to make these add up to 0 is if these two numbers are the exact same. If this is 3 pounds to the right, then this has to be 3 pounds to the left to add up to 0. And so that's pretty easy. Just set your opposing forces equal to each other. And as a matter of fact, let's add an extra horizontal force in there. Let's add a rightward force here at our pin, and let's do the exact same thing in the y direction. Let's add an upward force at our pin as well, and we can just keep this simple. We'll call it our force at our pin in the y direction, and we can call this rightward force our force at our pin in the x direction. And so now for this equation to be true, we have to also add our force at our pin in the x direction, which we just said is going to the right. And so then we can rewrite this equation to say that our rightward forces are equal to our leftward forces. So we got force 4 plus our other rightward force, which is force at the pin in the x direction, and those two combine to equal our force 2. They have to cancel out. And we can say the same thing for our forces in the y direction. We can say that our force 1, which is going downward, plus our force 3, which is going upward, and our force at the pin in the y direction, which is also going upward. All three of these numbers have to add up to 0. And if that's true, then we can say that our downward forces, which is just force 1, is equal to our upward forces, which is force 3, plus our force at the pin in the y direction. So if this downward force is 10 pounds, then these other two numbers have to add up to 10. So maybe this could be 3 and this could be 7, or they could both be 5 and 5. It doesn't really matter what those two numbers are. We just know they have to add up to force 1 in order for this statement to be true and this system to be in static equilibrium. But from there, let's talk about moments and rotational equilibrium, which follow very similar rules. So we can say the sum of all moments equals 0, which is called rotational equilibrium. Which is similar to static equilibrium, except we're talking about directional moments instead of directional forces. So in this case, our directional moments cancel out. That's our clockwise moments are equal and opposite to our counterclockwise moments. Now, we've learned in the past that a force needs some perpendicular distance from the pin to create a moment. And I really like this example because students can test the ideas in this video with nothing but your finger and a phone or any other objects that are remotely shaped this way. And one thing I've seen students struggle with is the direction of moments clockwise versus counterclockwise. So let's figure out how to tell if a moment is going clockwise or counterclockwise. And let's start with force 1. And if you pin this object down right here and apply some downward force, then this object would then rotate around our pin. Feel free to try this out. Take your phone or any rectangular object and pin it at the bottom left corner and apply a force right here and see which way it rotates. And so the general rule of thumb to find the rotational direction is take the direction of the force and turn it towards the pin. And then which way is this rotating? Well, that is a clockwise direction. And so we'll call this moment 1. And so we can do the exact same thing at force 2. We can create a moment 2. So we'll follow the direction of the force and the pin is below it. So we'll go left and turn it downwards. And so then moment 2 is rotating this direction, which is counterclockwise. And then force 3 is going up and the pin is to the left, and so we'll go up into the left. And if you look, this is also counterclockwise for moment 3. And then force 4 is going to the right and the pin is below, and so moment 4 is therefore going clockwise. And again, you can test this out just by taking your finger and pinning your phone at this point and then applying these forces in these directions. And you can literally see how a force creates some rotation. But something interesting happens with these forces at the pin. They don't actually create a moment. And let's break down why. And to understand why, there are a few rules about moments you need to understand. And the first rule is the pin is the center point. The structure would rotate around. And the word would is really important because if it's in equilibrium, then by definition, it is not rotating. And so it doesn't actually have to be rotating to have some moment. It just needs a force and a distance. Which brings me to my second rule, which is a force needs to have some distance from the center point to create a moment. And since a force applied at the pin by definition has no distance from the pin, then any force at the pin does not create a moment. And if this idea doesn't make sense to you yet, let me try explaining it to you with a little bit of math. We know that a moment equals a force times its perpendicular distance from the pin. Well, if you look at our force at the pin in the x direction, it has no distance from the pin. And so we can say then the distance of our force at the pin in the x direction equals 0. And likewise, our distance of our force at our pin in the y direction also equals 0. So whatever your force is, it's going to multiply by a distance of 0, which gives you a moment of 0. And feel free to try this. Take your phone and pin it at the corner and push it in random places. Anytime you push it up or down directly above or below your pin, your phone will not rotate. And the same is true if you push left or right directly to the side of your pin. There will be no rotation because the perpendicular distance to the force is 0. So I can't stress this enough. There is no moment at the pin. So that leaves us with only 4 moments. And they all have to add up to 0 if the structure is not rotating. So let's rewrite this out. We'll say the sum of all moments equals 0. And what are our 4 moments? Well, we've got moment 1 plus moment 2 plus moment 3 and finally plus moment 4. And moment 4 is going clockwise. Moment 3 is going counterclockwise, as is moment 2. And moment 1 is going clockwise. And so for all of our moments to cancel out and add up to 0, we have to set our clockwise moments equal to our counterclockwise moments. And our clockwise moments are moment 1 and moment 4. So we say plus moment 4 is equal to our two counterclockwise moments, which is moment 2 and moment 3. So if these moments are equal, that means the structure is not rotating. But that doesn't mean the moments aren't there. It just means they all cancel out. And so real quick, I want you to go ahead and underline that word would. Because remember, this structure is not actually rotating. By definition, these moments cancel each other out. But the moments are still there and still have a direction. We just can't see that rotation because it's canceled out by other moments. And so you have to sort of imagine which way the moment is going.